I mentioned earlier that the DFT can be thought of as a sampled DTFT. So first let's start by examining the equation for the DTFT. So the first thing you might notice is I left off the range of n. So we're going to assume that we have a finite length x of n. In that case, even though we're summing over all time, n equals minus infinity to infinity, it's 0 everywhere except for n is equal to 0 and minus 1. So if we have the finite length n, our definition of the DTFT looks like this. So now let's let omega sub k be 2 pi over n, so nice even steps, times k. And we'll do this for k equals 0 up to n minus 1. No surprises there. Maybe these are the only frequencies we're interested in. I hope so, because it's the ones we're going to get. So now if we take our DTFT and evaluate that at omega equals omega k, then we have the sum from n equals 0 to n minus 1 of x n e to the negative j 2 pi over n k times n, which is identically equal to xk. So, in summary, we made two assumptions. We first assumed that x was finite length of n samples, and it started at 0. In that case, our DTFT summation range collapses. Second, we assumed that we said we only want to sample it at evenly spaced samples, or the period of our samples in the frequency domain is 2 pi over n. When we do that, we get our DTFT. So here's an example I just cooked up in MATLAB of a simple sequence that is 7 points long. And in the upper window, in the lower window, we see the DTFT in blue and the DFT of that same sequence in red. So one thing to notice here, the axis is normalized to 2 pi in the lower part because it's kind of easier to understand. So for this particular one, then we would have this point corresponds to pi, and we have the positive frequencies there on the left hand side, and then it's periodic. Remember, the DTFT and the DFT are periodic, and so what we're seeing here are the negative frequencies showing up on the right hand side between pi and 2 pi. So we could have done this either way. This could have shown up down here just as easily as it did over there. And since the DTFT is periodic and the DFT is defined from 0 to k, it's more common to see it in this format that I've seen here than the one that we've typically been showing, which shows the positive and negative frequencies, like so. Okay, so here we go. I guess I should label some of these points. This is the DTFT of x of n. And this works, remember, because x of n is finite in length. Here's the DFT of x of n. And there we go. Now, what happens if we want more samples of our DFT? Right now we have k samples, And you must admit that if you look at this, it's not enough to give you a whole lot of information. Since we've already shown that the DTFT basis is an orthogonal basis, it has k basis vectors, and we have dimension k, or I'm sorry, it has n basis vectors, capital N basis vectors, and since x only has n non-zero values that we are concerned with, then we know we can perfectly reconstruct our signal x of n from these few scattered samples that we have of our DTFT. However, we often want to know more what frequencies are there. What's the shape like? Is there a way we can do that? And of course, there is. We can say, let's just use a larger n. Well, actually, let me back into it this way. We'll use a larger n prime when we come up with our samples, like this. Okay, let me see if I can explain this more clearly. We have an n, a value n, that describes the length of x. So we're now going to, and we use that same value of n when we sampled our DTFT. We said omega k was equal to 2 pi over n times k. But now we're going to say omega k is equal to 2 pi over n prime times k, where n prime is larger. So that gives us smaller steps that we take in frequency, and effectively more frequency samples. So in this case, we now have x of k is equal to the sum from n equals 0, and we're just going to have our old n minus 1 up there because x didn't get any longer. But we will have e to negative j 2 pi over n prime kn. So there we have it. That doesn't give us a whole lot of insight though, does it? So what we're going to do now is a little trick that's used all the time. In fact, I used it while generating the plot right up there. And that is, we need to bring n and n prime somehow into agreement so that we can use all the math that we've developed so far. So the first thing we note is that, well, if we redefined x to be longer so that it was n prime long, then we could do that. But where do we get these extra values of x, and won't that affect things? Yes, it will affect things. So let's be really careful about how we do this. We note that this is the same as taking an n prime point DFT if our original x had a bunch of extra zeros in it. As I just say the sum from 0 to n prime minus 1 if x of n was extended by adding zeros. And we call this zero padding. Let me write that legibly and see if that helps. So why can we zero pad? Well, let's go back up and look at what we initially were doing when we sampled our DTFT. We initially had the sum over all n, but we said that since n was equal to, or x of n was equal to 0, everywhere outside of this range from 0 to n minus 1, we could just sum from 0 to n minus 1. Well, there's no harm in summing from 0 to something larger than n minus 1. We're effectively adding in more zeros. So it hasn't changed the sum any, but it has changed our ability to analyze what's going on. So if we do this, we end up essentially having finer samples. That's what happens with our 2 pi over n prime. But other than that, nothing else has changed, except that it now looks like we were taking the DFT of a sequence x of n that's been padded by some zeros. By doing that, our DTFT is longer, we get more samples on frequency, but the DTFT that we're sampling is exactly the same as it was before. Okay, so here's an example of our same waveform from the previous page. And I've now zero padded it out. I could have plotted it differently to show those zeros, but I can draw them in just as easily. There we go, 14 zeros. When we take the DTFT, the DFT of this one, we now get samples that are much more densely spaced. So let's compare this side by side. Copy, paste, move that over there. So you can see that we now have more samples. In this case, we took our 7-point sequence and we zero padded it out to 14 points to get this. So we have twice as many samples, but we could zero pad it out as far as we wanted to go. So I have the MATLAB code for doing this down below. Let's go through this. First, it's not commented. I just threw it together quickly while actually making this lecture. So first we define our sequence x as shown above, and then I want to have the DTFT. Well, where do I get the DTFT? I don't. I can't really very easily calculate the DTFT. Since I have a short sequence here, I could figure out an expression for it, and we could go from there. But it's much easier to just create a sampled version of the DTFT. I mean, that's what we're doing. And so I take the DFT, which is written here as FFT, for the fast Fourier transform. We'll talk about that more later, but what you need to know right now is that the FFT is the DFT. It's just a fast way of computing it that saves going through all the sums of these complex numbers. So we will actually develop the FFT later in the class, but for now we just use the FFT to calculate our DFT. And then to approximate a continuous in frequency, DTFT, I told it to zero pad x to 100 or 1024 samples. So zero padding is so common that it's the second parameter for the FFT. And so then I could plot the DFT or the DTFT later down below by plotting the absolute value of capital X. Found the DFT of, and I did x of 7 just to denote that this is the 7-point DFT of x and plotted those. One thing that you may find interesting, if you know any LaTeX, you can tell MATLAB to use LaTeX as an interpreter, and that lets you have mathematical expressions in your X labels or your titles or Y labels and so on. So we plotted those two on top of each other. Down below, we just zero padded X out to 14 samples and plotted the same thing, except now that we're plotting this one. So we have more samples in frequency. One last thing that I almost forgot to bring up is what happens with negative k and what happens with negative frequencies. So the frequency of x of k is omega k, which is 2 pi over n times k. And that corresponds to our term e to the j 2 pi kn over capital N. What if we had a negative n? Obviously, we have negative frequencies in the DTFT. And so let's just look at what happens if we take a positive k and we make it negative. So we would get e to the negative j 2 pi over n negative k times n. This is e to the negative j 2 pi over n kn with the negative out front. Well, we can always add 2 pi to anything. So let's, in the exponent here, so let's do that. And we get 2 pi over n. And we'll get rid of that negative out front. We'll put it back in there. Say n minus k times n. So we've just added 2 pi over n times n, which is 2 pi. And so that's not a problem. And now apparently we have a new frequency. So negative k, I'll say the frequency negative k corresponds exactly to the frequency n minus k. So negative frequencies show up in the larger DFT coefficients. So I've just used the word coefficients for the first time. This is consistent with our view of the DFT as a linear algebra construct. In that, what are the coefficients? So our x of k terms are coefficients. They are actually given lots of slang terms in common usage, which sometimes provides some interest. I was testifying in a legal case where a patent used the term bins for the coefficients, and often they're thought of as frequency bins. I don't see that much in the literature, but the court wanted to know, well, what is a frequency bin? And they wanted a formal definition so they could evaluate the claims of the patent. And so I checked many textbooks, and almost nobody ever mentioned the term bin, but yet it's common in everyday usage to talk about frequency bins. So when someone talks about frequency bins, they're talking about x as indexed by, our DFT as indexed by k. So there would be k frequency bins, and each of those, the signal at each of those values would be the value in that frequency bin. I'm not sure still where it came from, but we finally found some references, and we're able to at least clarify that for the court. So sometimes they're called the DFT coefficients, and sometimes they're called the bins, and other things as well, and you can pick that up by context. But the yeah, I guess that's it. So we'll move on to DFT properties next.